All right, wonderful. Welcome everyone. Welcome to today's session, labeled Hands-on Simulation Series on SimCenter Flow EFT. Let's just jump right into it. And so today, the presenters are going to be myself and David. David, could you go to the next slide? So essentially, I manage the pre-sales team at Maya, focusing in the Americas market. And David, do you want to introduce yourself? Go ahead.
Yes, my name is David Stevens, and I've been at Maya now for about 7 months, and I'm a technical pre-sales engineer here. And before I came to Maya, I was in research and development for turbo machinery and heat exchangers.
Perfect, wonderful. Thank you very much. So most of us over here, are current customers. Some of us are, people looking into Maya and attending the session. So maybe before we even get started, just a few words. So, but essentially, David, go to the next slide. So essentially, Maya, we are a software-driven engineering solutions company. We are 250% strong company with 75% of us being scientists and engineers. Though we started in space 35 years ago, over the last 3 decades, we have expanded across various industries. So we have a interesting relationship with Siemens, where we are value-added resellers, but also OEMs. We develop 30 plus software modules for Siemens, author them, and they're embedded within the tool set. So moving to the next slide, in terms of the solutions we provide, obviously simulation is where Maya grew up, but over the years, we've expanded to every other domain within the engineering digital space, starting from design, manufacturing, so computer-aided manufacturing, PLM, so deployment of PLM solutions, namely Teamcenter, automation optimization, custom development, as well as AI and machine learning. So a lot of our customers, they have these vast data sets and want to make sense of this data, or even develop anomaly detection tools. So we have helped implement solutions across all industries. So as I mentioned earlier, we are resellers of the Siemens tool sets, and so today we're going to focus on the SimCenter portfolio. So the SimCenter portfolio is the simulation center, or all the tool sets within the Siemens ecosystem that enables you to create a digital twin of the simulation domain. There are three specific domains that simulation is focused within SimCenter. We have CAE simulation, that's everything related to 3D, system simulation, that's model-based system engineering, and physical test. Now, one of the key things about SimCenter is that you can combine these different multi-physics capabilities to do multi-scale, multi-phase, and multi-domain analysis. So just an example, if you're modeling, as David mentioned, he's an expert in heat exchanger, he would want to do it in the 3D world. So modeling the 3D, in the 3D world, you would have thermal flow, but also you can do acoustics, structures, dynamics. So these are all the various domains that you can implement within the 3D space, right? But as I mentioned earlier, we can also do it in the system world, where you can use 1D networks or the equations to model the piping systems, then combine the two domains together to do quite complex simulations, which otherwise would be too difficult to do in full 3D. So today we're going to focus on thermal flow. And within the SimCenter portfolio, what's important to note that there are multiple solutions depending on the user group and the people using the given simulation. So regarding the thermal flow, we have solutions that are aimed for analyst, expert users. We have simulation that are aimed for those focused using NX or SimCenter 3D, but we also have simulation tools available for designers or CAD users. As you can understand that, for simulation for a CAD designer is quite a forfeit, because running CFD simulations specifically requires some sort of background knowledge in CFD. Setting up the simulations are very complex. And so today's presentation, or the solution that we're going to focus on today, is for designers or folks with a non-CFD background to enable and use simulation. And that idea of being able to bring simulation up to the forefront of the design process helps reduce significant costs and time saving. And I'll pass it on to David to now essentially explore today's presentation and give us a full overview of what the solution is and how it's implemented. David, it's all yours.
Well, thank you, Yapis. And thank you for everybody for attending and joining us today. As Yapis was saying, we're looking at Flow EFT in terms of and targeting towards the designer. And so one of the best ways to look at this from the beginning is looking at a typical design workflow. And actually, do we want to just go over the hands-on simulate series real quick too?
Sure.
Yeah.
Yeah, exactly. Apologies, folks. So before we jump into it, maybe give an overview of what we're going to accomplish. And as David said, the first session today is going to be on SimCenter Flow EFD, this given solution, but it's a part of a four-part series where we have a session every other month. So this one's just going to focus on the product and the demo we're going to do in IGBT cooling module. But then this given product also has specialized modules. So we have one for the electronic industry where we'll do a detailed PCB analysis, look at also structural analysis of the PCB board. We're going to do another one on the EV industry, right? And then we're going to do where we're going to look at battery pack modeling specifically, but also look at any other technology where we're able to embed electrical circuits and model that in your CFD simulation. And finally, we're going to look into HVAC simulation or building technologies and anything to do with flow analysis. So within a Flow EFD, yes, we have the base modules, but we have specific add-ons that are focused, that are industry focused, depending on what type of simulations are being run. So yeah, David, take it back to you with regards to starting the first session. That's the introduction to SimCenter Flow EFD.
Thanks again, Yafis. So I think one of the big buzzwords we'll use today or phrases is front-loading simulation, as you saw probably in the advertisement for this webinar. What is front-loading simulation? And as we talk about what that is and how that can be applied to an engineering designer and not necessarily a CIE specialist or a CFD specialist. So what is front-loading simulation? Let's take a look at this from a typical design cycle. A typical design cycle, you start out with conceptual design, you further and further refine your design, and then you eventually get to a prototype and maybe go to manufacturing. And certainly we know that it's much easier to make changes in your design early in the design stage under conceptual design, before any prototypes have been made, before lots of time and money has been invested. And that's where it's easiest to make the change. And that's where it's also easiest to impact the design using simulation. And as I said before, you really want to make those changes during the conceptual stage, before we develop prototypes, manufacturing tools. The worst case scenario would be that you have manufactured some expensive prototypes, or you've even delivered something to a customer. And as we know, many engineering processes today, for a long time, it's been, prototype. How soon can we have a prototype? And how soon can then we get the product out the door? But prototypes aren't always easy. Prototypes can sometimes now be more expensive, and lots of times be more expensive. And this is for a multiple set of reasons. Today, as we have, certain limitations on people gathering in groups and all of that, and also supply chain issues. Prototypes are more expensive and often harder to test. So what could we do differently in an ideal world? We could see that maybe we do front-loading simulation earlier to look at and make design changes based on our design criteria early on. We can get near almost real world data from our simulations that can really impact our designs, and so we don't have to make changes later on down the road when we have a prototype. So that's what front-loading simulation and really is, and that's what we want to focus on today in terms of Flow EFD. So what are some of the customer benefits that we've seen so far of companies that have adopted front-loading simulation? One of our first customers, Renault Designers, they equipped their engineers, their design engineers, with simulation tools, and they were able to reduce their cost in their lighting division by 50% within 2 years by equipping their design engineers with simulation that could be used effectively to make changes early in the design phase. Another company, Jazzo, they develop protective housings for various applications by implementing front-loading simulation. They were able to communicate their designs to the customers in less than 1 day. This made a savings of 3 weeks over their previous process, and also they were able to get not be reliant on prototype testing as much. Another company, Mitsubishi Materials, they were able to drive innovation through front loading as well. Without any expert, CAE analyst expertise, their designers were able to increase the flow rate in their cooling systems for their advanced cutting tools by 11%. Another known customer through front loading was able to automate their simulation process, and they were able to reduce errors and develop engineering process that was 100 times faster than what they were doing before. So clearly there's value here in front loading simulation. It's important to note that front loading simulation is multi-domain and can even be simply accomplished by redesigning your existing design process. It doesn't have to be something that completely ends up everything. It may just be implementing this early in the design process. And today, we believe that the best way to demonstrate this for you is to show a front-loading simulation workflow from start to finish in a real engineering problem. So we'll go ahead and go to our first poll. Yafis, if you want to go ahead and bring that up. I'll give you a second to think on that.
David, apologies, I lost my internet, but
no, it looks like the poll's up.
Perfect, wonderful.
So it looks like a majority of the folks here today, they have about 41% saying they don't currently use CFD analysis in their process. About 24% saying that they use it early in the design stage, which is good, and then 22 say they use it in the initial design phase, and 16% say they use it in all phases of design. These numbers are evening out a little bit more here, but still the majority is saying that they don't currently use CFD analysis in their current process. And today, I think we could probably show you that it would, using a product like FlowEFD that's very designer focused, can be easy to implement and get good results out of that can directly impact your design. So from there, we'll go to what we're looking at today. So let's take the example of an IGBT module. And an IGBT module, it requires a cross-domain of engineering, and that's why it's a good problem to look at for us today. We could have chosen a bunch of different things, but this takes into account heat transfer as well as fluid flow. And if you wanted to take it further, it could even be taken to structural design as well. But this, as I said, is cross-domain. It looks at thermal flow. It also includes electromagnetics and electronics. We won't be looking at that particularly today, but FlowEFD does have capability there that will be seen in some of the later webinars. This device is used across a wide range of industries, such as electric vehicle powertrains, wind turbines, refrigerators, and really the primary function of an IGBT is to rapidly switch on and off high current loads. And certainly because of this, you can generate kilowatts of heat by doing this. So liquid cooling is really one of the only ways to keep these chip temperatures down to an acceptable level where they won't suffer damage. Certainly you can see here, if this next animation comes up here, is that one of the major causes of failures within IGBTs and electronics is overheating. So, looking at that and understanding that before you create one of these devices and send it for manufacturer or prototyping is quite critical. So next, let's take a look at the factors that go into designing one of these units. So when designing an IGBT, you certainly want to increase your maximum power output of the unit and the load capability, but you also want to make it reliable, and most importantly, you need to keep that within the thermal constraints. In cooling systems like this, in order to keep these cooler, you can increase the flow rate, and that will drive the temperature down in the system and drive the temperature down to the chips. However, you are going to suffer a lower pressure drop through the system, so you're going to have to use a larger pump to drive your coolant, and that's a trade-off. So this is kind of one of the classical heat exchanger design balances, which is I want to maximize my cooling, but I also have to be careful about not increasing the pressure drop so much that I need an enormous pump to drive it and lose a lot of energy there. One of the typical workflows that we've seen in IGBT manufacturers is that they'll get the design considerations, the product specifications will be delivered to the designers, and then the designers from there base their design on past designs, and therefore the validation design, meeting the engineering requirements is relied on previous physical testing and maybe not so much on simulation. And then maybe they do this simulation, but maybe it's done late in the design cycle when it's really hard to change something and very expensive to change something. And merely at that point, simulation is just kind of a rubber stamp. And we can implement this earlier in the design phase. We'll harp on this all throughout this webinar is how can we affect design changes and how can we improve the design. And as I said, you really don't want to be detecting those faults in the design late in the design cycle. And when that happens, engineers have to return their iterative cycle. They have to make those design decisions over again. And as we said, that's very expensive. And that's oftentimes at Maya, where we see companies come to us asking us for help. And just showing a little bit of workflow here, but that's where we want to implement that front-loading simulation is early in the conceptual design phase. And next, we'll go to our next poll.
Perfect, wonderful. I am going to launch next poll. So the next poll is essentially, what is the greatest challenge you face when performing a CFD analysis? And so these are some of the major challenges. Obviously, some of you might have all of them, but think about what's the major one. Model geometry decomposition abstraction. Meshing itself, creating that mesh between the fluid and solid interfaces, developing accurate boundary conditions, model convergence, solve time, and computer resources, as well as post-processing. Now, it's important to note that a lot of the times, and we saw a majority of the people not essentially do any sort of CFD analysis, and this is some of the major challenges. And at each step of the way, I'm quite positive that I've faced problems at each step. And this is sort of what we're trying to alleviate, is that these are challenges that you'll face with a general CFD or an analyst tool. But however, with what David is going to show today, we're going to show we're going to show solutions to each of these challenges. So looking at the poll, we're equally divided between meshing, developing accurate boundary conditions, and model convergence. Not much on post-processing and model decomposition. Yeah, that makes sense. But in a sense, we would say that these are all equal challenges. So I'm just going to give it another 5 to 10 seconds for people to put in their votes. I personally feel that meshing is something that I deal with a lot, especially when you want to mesh the solids and the fluids, and if you have small gaps or small edges or small surfaces that are thin, how do you mesh that to making sure that the mesh quality is pretty good? And we'll talk about how FlowUFD resolves that challenge. So I guess that answers that. I'm going to close the poll, and we can see that the results. I'm just going to quickly share those results for the folks out here on the call. And this is what I was seeing earlier. So an equal distribution between meshing, developing accurate boundary conditions, and model convergence. So go ahead, David.
Awesome. Thank you, Yafis. And yeah, I would certainly agree with Yafis. I think in some of my past experience, some of the most time-consuming and frustrating points have been trying to make a good mesh, and it takes a lot of iterative, sometimes some trial and error to get a mesh that's acceptable and can run a good converged solve. But let's look at a bunch of these challenges overall and what this looks like for if there's a designer we're going to opt to adopt a CFD process. So the first thing we'd be looking at is learning a new environment. Certainly anytime in analysis tools or CAD tools, all even UI environments are different. So certainly anytime that happens, you have to learn a new GUI, you have to learn new terminology, new commands, whatever it may be. This certainly creates a barrier to entry in terms of analysis, and that would certainly be the first one. Secondly, traditional CFD analysis often does require simplifying geometry. This is also known as geometry decomposition. Doing this without affecting the answer of what you want to learn about the simulation isn't always straightforward. So that takes a bit of work, and then so there's always a trade-off between how to make the geometry more simple to get an acceptable mesh, but also not changing it so much that you're affecting your answer greatly. So that's another challenge. And that comes from just sometimes a lot of experience and a lot of work in the field in some of these models. Third, designers really need to have the knowledge on setting up the physics problem, may it be CFD, thermal, or even structural. So that often requires experience and maybe sometimes an advanced degree. So that's really another barrier to entry. Fourth, successful meshing in the computation, as I said, is often time consuming. It can be an iterative process. It can require detailed knowledge of best practices for meshing, depending on what type of problem it is, whether it's a low Mach problem, a high Mach problem, where the flow gradients are, etc. And looking at that in FlowEFD becomes less of an issue. Fifth, generally most CFD models, get a little behind here, most CFD models do not converge the first time, at least in my experience. And achieving a converged solution often requires adjustment to numerical algorithms or even sometimes going back and adjusting the mesh. And then six, another challenge is how can a designer interpret the results to make changes and improve the design performance? This often requires collaboration with analysts. And then finally, what about design optimization, which design optimization often could be considered the holy grail of engineering simulation? How do you put a bunch of parameters into a simulation and say, okay, give me the best design? If you can do that and not have to, do a whole bunch of manual iterations, that can be a major time saver. And passing that task on to a designer probably isn't economical, and that's probably where you would bring a typical focused CAE analyst into the problem. These engineering problems are all complex and multi-domain. Requirements for components are always changing when different systems are integrated into a prototype. I know that's something that I always struggled with in some of my past work, is that as soon as something was analyzed, something would change. So having the capability to perform quick changes and rerunning the analysis is always important. But really, and overall, is how do we use front-loading simulation to redefine our current engineering process in order to be able to adopt it. So as I said, the first challenge in front-loading simulation is that the designers would need to learn a new environment, and that's what we'll go over here first in the demo. And we'll look at that in terms of context of an IGBT. Before we do that, though, we should talk a little bit about what FlowEFD is, and let's get introduced to our tool. So what is FlowEFD? FlowEFD is a front-loading multi-CAD embedded CFD tool for designers, but it also could be used with experienced analysts to do some quick work as well. It's not simply just for designers. It has some very powerful features in it that I'm very impressed with. As I've stated previously, front-loading is the concept of performing your simulations early in the design cycle to maximize the impact and catch issues before late-stage validation phase. There are several features to differentiate FlowEFD from other tools on the market, and this slide kind of aims to identify some of those. It is a general purpose tool that can be used in a wide range of flow and heat transfer problems, as well as many other applications as well, which will be highlighted in some of the later webinars as well. One of the really big things here and that differentiate FlowEFD is that the mesher and solver have unique proprietary technologies which facilitate the streamlined CAD embedded approach of this product. The result of which is a drastic reduction to barrier to entry and overall CFD simulation time. The tool is available in 5 versions to support MCAD workflow. So you do have it available for, as it's shown there, CAD embedded in NX, Solid Edge, CATIA, and Creo. Today we'll be looking at the NX version for this demo, but the process is identical for other MCAD systems. Just as we said earlier, that there really is a wide variety of applications that FlowEFD can be applied. Even some, very complex, things like cavitation, free surface, supersonic analysis. One of the things that impresses me the most about this product, just from my previous background, is its ability to use real gases. So if you need to do something with refrigerants or or a type of gas that the properties change quite a bit through the simulation. It has the direct ability to use NIST gas, NIST lookup tables in your engineering simulation, and that's a very powerful feature. But you can see here an overview of everything, and even have some work with rotating equipment here. So there really isn't a whole lot FlowEFD can't do in terms of a general design application. So let's take a first look at our demonstration. And this is kind of our roadmap for today. The workflow will mirror the actual steps taken to go from raw geometry to CFD results using the software. We'll be taking a look at each step in a little bit more detail, and we'll be able to highlight some of the unique features of FlowEFD as we do that. As I mentioned previously, we'll be simulating an IGBT that is liquid cooled. And as we said, we can find this typically in an electric vehicle or renewable energy application, any place where there's lots of current that needs to be switched on and off. As we can see in this slide, this is a typical result visualization, and you can see the temperature variation on the free surface of the solid bodies, as well as the flow stream lines on the other side of the heat sink. And as we go, well, the first step that we'll cover here will be CAD integration. That's really where we want to start from a design perspective, is how does this integrate within the current CAD environment? As we said, that FlowEFD in this demonstration, it's natively embedded into NX, but it also can be natively embedded into Solid Edge, Creo, and CATIA. There also is a single standalone version available if you don't want to have it embedded directly into one of your CAD tools. So this means there's no need to transfer geometry from your current CAD into a geometry tool, and it's much easier and more efficient to update changes. And we'll even show today how that CAD tool can do optimization directly working with the CAD tool. And going into that, all of the assembly and parametric definitions of the part and assembly are contained within the file. You don't lose them. This is much different compared to using something like a step file format, where all those parameters are stripped out and you're just left with a solid that nothing can be changed except for maybe if you define some new parameters or new commands within your CAD file, but you don't get that native design intent in your CAD system that comes over. The image we have up here, this is the flow region for our IGBT today, and we'll be showing how that's extracted and how easy that is to do. And that's the case. Let's go ahead and jump into it. So we have here in the NX environment is our IGBT. It's coming up for me for a second. My computer's just being a little slow, so I'm going to take a sip of water. And you can see here we have some translucent bodies to be able to see through this entire thing. And we can see on the bottom here our heat sink, and I'll show you in a little bit this more detail once my PC catches up. There we go. And on the top where we have our silicon chips for the diodes and the IGBT. To have a little bit more of a detailed look, we'll just go ahead and explode this. Still running a little slow. We'll go ahead and explode this, and really what we want to show here is that there's a lot of different parts in this, and actually kind of more than that you would just see from the naked eye. And this model includes not only your silicon, your chip carriers, the silicone potting around the entire thing, but also your thermal interface materials for each chip, as well as the chip holders. And then, of course, looking at our heatsink interface here between the solid and the fluid regime, and it also includes our O-ring. You'll also notice here that we have caps on the inlet and outlet of the flow domain. Those have been automatically created for this demo, but we'll show you how easy that is to do real quickly within the FlowEFD environment. So go ahead and just pop this close again. Another really important feature, we saw that O-ring in here. And if I do a quick section through this and zoom in here, we can see that there's a geometry interference between our O-ring and our solid body. And normally within most CFD tools, you would need to eliminate that interference before the simulation could continue, because it would cause a numerical error within the solver. if you were to mesh those and they existed within the same space. In this case, we don't have to worry about that, and I'll show you why here shortly. From that, I'll just also go into our heatsink here, because this is going to be an important piece when we look at optimization. But this heatsink is designed using the NX expressions. Should open up here real quick, and we can see here that these heatsink pins have a defined diameter, draft angle, and pitch. And this is controlling directly parametrically all of these pins in the model. And we're going to go ahead and use these later on to run an optimization to reduce the pressure drop in this system and also increase the maximum heat transfer. So that's really one of the big pieces. By keeping this connected to the CAD system, we contain that and we keep it for the simulation, and we're able to utilize it for optimization. From there, I'll just go ahead and I'm going to go ahead and open FlowEFD. There's two different ways you can launch FlowEFD. Before I do that, I'm going to get rid of this section, and we can just go up here and to our file, and we'll go to all applications, simulation, and FlowEFD simulation. We also can just hit Control-Shift-F if we'd like, and that's sometimes easier than navigating through the menus. So now we're in FlowEFD. It's been launched here. We have our FlowEFD navigator up here, and then we have this flow analysis ribbon bar along the top. And you can see everything so far is grayed out because we haven't created a new simulation yet. But before we do that, we should really check our geometry and make sure that we have an enclosed flow region. So if we go ahead and do our check geometry, it's going to say that we need our resolve component. It's going to resolve all our components for us, meaning it's going to load all of them in. So if you are working with a large assembly, it can do that, but it might take a minute. So this is opening right now, but as I said, we want to check that flow domain. We can check for how large the flow domain is in terms of volume. We can also check for how large the solid domain is in terms of volume, and we can also view it. Looks like it closed on me. So we have the option here to look at internal or external flow. This is going to be an internal flow, and if I just go ahead and hit check, it's going to run the check, and it says it's successful. We have our fluid volume here, and we have our solid volume, and then I can also view our detected volumes here. So you'll notice though, it's detected multiple fluid volumes here. However, we don't have to worry about that. FlowEFD will automatically ignore this extra volume here that is just dead airspace. And we could look at that if we were worried about natural convection or something like that in there, but in this case we're not. We're going to go ahead and say that that's all adiabatic. We also have those gaps where the O-ring exists, and FlowEFD will automatically ignore that if we tell it to in our wizard. So from there we'll just go back and give a little bit more on the next steps we would do in FlowEFD. So just jumping ahead here. So what we just saw is that there's a CAD embedded nature of the software and how designers can leverage their pre-existing CAD skills and their CAD models to perform CFD analysis. So it's a direct integration, it's extension, it's not a different environment. The benefits of having a CAD embedded approach is that there's minimal geometry simplification necessary, and this is especially true with FlowEFD that we'll see later. Geometry changes are detected automatically, so if you were to run this analysis and have everything set up, if you updated and made a change to one of your parameters, you could automatically rerun the simulation without having to do a whole bunch of work to retool your model. And the familiarity with the CAD interface, as I said, a logical extension for the CAD designer. So what's next? Our analysis setup. So we've now prepared and checked the geometry, and we're ready to set up the analysis on the assembly. We can create the FlowEFD simulation using a wizard, or we can do it manually. To start, usually the best thing to do is using the wizard process, so we'll go ahead and do that today. So we'll apply flow and thermal boundary conditions directly to the CAD parts, and these can also be we can also use, if you have a certain engineering database that you have at your company, these can also be imported into FlowEFD to use for solid materials or fluids. But for now, let's go ahead and jump back into FlowEFD, and we'll go ahead and do the setup that we need to. So we'll just go ahead up here and select our wizard. This is a fairly short wizard. We'll have to give our project a name. We'll just call this IGBT. And we'd have the option for doing certain CAD configurations, but we're not going to worry about that today. So we'll go ahead and hit next. Here we can define our units. The unit system that you can define is, it can be 100% customizable, or it can be pure SI. You can make it whatever you want it to be. You can even enter different units into the dialog boxes later on. As long as you specify the units, they'll automatically be converted to the current unit system. So that's one thing that's very nice. You don't have to always do a quick conversion. You can just enter it and it'll automatically do the conversion for you. Today, we're going to go ahead and just use this custom defined system off the USA units that I've named for this demo, just to make sure that everything lines up. But you can see when you look at these, how all of your units are defined for your current unit system. Once that's all set, we'll next look at what type of analysis we're doing. Here we're doing an internal analysis, and we're looking at fluid flow, but not only that, this is a conjugate heat transfer analysis, so we'll also be looking at conduction as well. And as I mentioned earlier, we won't be looking at cavities with outflow conditions. So we won't be, if a boundary, I should say, if a cavity doesn't have a boundary condition applied to it, Flow EFD is automatically going to ignore those fluid regions, and that's why I have that checked here, and that's going to eliminate that closed off little fluid space around the O-rings, etc. Next, we need to define our materials for our fluids or our gases. In this case, we'll just be looking at water. So we'll click on water and hit add. We have that selected there. We're not worrying about cavitation when we're doing a laminar turbulent flow. And then we need to just predefine a metal. We're actually going to import our metals automatically from the NX CAD environment, so we don't have to meticulously go through this and select all of our materials, but it does need a default material selected, so we'll just select aluminum there. Next, we can define a global boundary for thermal conditions. So for this analysis, we'll just be looking at an adiabatic solution. We're not releasing any heat to the external environment. We also could define a default surface roughness for walls. In this case, we're just going to leave that at smooth, so 0 microinches, but these can also be identified at locally later in the solution if we wanted to. They don't have to be global. Last, we need to define our initial conditions for the solution. So anytime one of these solves happens, the solver has to have some place to start. In this case, since we're looking at under hood vehicle conditions, let's say in this analysis, we're going to define our solids all initialized at 65 degrees C, and we'll do the same thing for our fluids at 65 degrees C. And that's it for the beginning of our wizard. Once I hit finish, it's going to populate our tree here for this first simulation, and you can have multiple simulations, or I should say projects, within that that can be created. Our next piece is, well, first let's look here. We noticed that this box here has showed up, and it's going around this entire part. And this is giving us an idea what the domain of the problem is. And if this were an external analysis around a sphere or something like that, you could manually change this to be or wherever you want the flow to be, say if it's an external flow. Today it's an internal flow, so it's just bounded based on the ends of the solids and also the fluid domain on each end. So go ahead and hide that though. We don't need to see that right now. But the next piece is we need to assign our solid materials to all of these parts. The easiest way we can do that in this case, that materials have been defined to a majority of these parts within NX. We can just go to solid materials, import data from model, and it detects all of our materials identified on these parts. Normally, if there wasn't like a particular property correctly defined, it would give us an error. We don't see any errors here. Everything's good for our solid materials, so we just go ahead and hit import. You can see that all of our materials have been imported for our parts. The only thing that hasn't been defined is our silicon for the IGBT chips and the diodes. And those are easily defined as well. I don't even need to click on them because I can use this tree within here. And I can just go to insert solid material. And in this case, they're going to be predefined semiconductors that are silicon. And select body, I can just go to my assembly and select my chip assembly, and select my diodes, And there's 3 of those, and the IGBTs, and you can see them highlighted there. And I have now imported, and I now have all of my materials, and I can quickly jump back to FlowEFD using the icon that's now available here. And we can see silicon there that's defined. From there, we need flow conditions for the fluid regime or the fluid domain. In order to do that, I'm going to hide this casing so that I can select my boundaries here on these CAD parts. And these lids are created using the Create Lid tool. As I said, they've already been created, but all I need to do is to create the lids. It'll give you a warning if you need lids within your model. Click Create Lids, and all you have to do is click on the surface that's bounding the domain, and it'll automatically create the lid. But I want to input flow boundary conditions for this. On my inlet is going to be on this side, my outlet is going to be on that side. To define a boundary condition, I select the boundary condition icon up here. And this gives us pretty much all of our flow and pressure boundary conditions or wall boundary conditions. In this case, we're going to be using an inlet volume flow. And I'm going to to do that, I'm just going to select this interior face at the flow domain, or at the termination of the flow domain, and I'm going to define this at 1.5 gallons per minute. And just hit OK. And that shows an inlet here with those red arrows. And next, I'll select that again, and I will define an outlet pressure. In this case, for simplicity, I'm just going to select an environmental pressure, which environmental pressure simply means the environmental pressure that was defined in the settings for the wizard. In this case, it's just atmospheric pressure, but also the thermodynamic condition is the initialized temperature that we set in the wizard, which is 65 degrees C. All right, so now we have an inlet and an outlet. Doing so, we'll be able to see the pressure drop across the system when it solves. And next, though, we need to apply heat loads to these IGBT chips and as well as the diodes. To do that, we can go up to our sources here, and we have a bunch of different options. We have a surface source, a volume source. You start to get more complicated getting into specific thermal resistances and electronics, but today we'll keep it simple with just a volume source in these chips. And we'll go ahead, as I did before, and just select the IGBTs from the assembly tree. And the heat load I'm going to place on these IGBTs is a total of 360 watts, and those will be split across all 6 chips. So those are done, and then I'm going to do that again, except this time it's going to be for the diodes. And these diodes are going to be a little bit less power at, oops, wrong box. We want volume source, not boundary condition. These are going to be 144 watts. And I'm just going to go ahead and select the diodes, apply that. And now we have everything here that we need for setting up this simulation. So if we just jump back to our PowerPoint here real quick, just to recap, we saw that the analysis was set up in the NX environment using a wizard-driven process. The analysis boundary conditions are applied directly on the CAD parts. There's no command line that we need to do or anything like that, and it's quick and intuitive so that it can be applied as the designer would see it using their design intent. Now we'll just jump into our third poll real quick.
The usual on the mute thing. So let's go to our third poll. You're going to see it up on your screen. Does your work require a CFD software with any additional or special capabilities? So far, so forth, we've talked about conjugate heat transfer. We've talked about just, thermal flow analysis. But clearly, when it comes to CFD, there's more than just that. Then there are multi-physics capabilities that are required in most cases. So looking at combustion, two-phase flows of particles, looking at fluid structure interaction, or non-ideal or non-Newtonian fluid properties. And I guess the reason why this question was even asked in the first place was because so far, we've talked about conjugate heat transfer, and that takes away the breadth of the solutions that majority of the folks in the CFD world have to resolve. But fluid structure interaction that is a huge other component when looking at, let's say, thermal warpage or any other effect of thermal expansion. And so the reason why this is actually out here is because within FlowEFD, even though today's webinar or today's session is just a thermal flow problem, we have the capabilities of resolving all these other physics within FlowEFD, which will come in the upcoming webinars. So it's just sort of a small nugget to those who, to get you guys to attend the next sessions as well. So um, so far so forth. By the way, David, this is amazing how you can easily extract the fluid volume, which is like one of the biggest pains that I face myself, and the fact that you can deal with such complex geometries. So well, let's give it a few more seconds before we close the poll. So we'll get everyone to vote out here and hit close. Okay, so I'm
All
gonna
right.
share the go ahead, David.
No, I just say, yeah, but it looks like majority of folks that voted congregate heat transfer is their major thing, and needing that extra capability, and
Yeah,
that can be kind of intimidating, going from just a basic volume only CFD analysis with a fluid domain only going to a solid domain. And FlowEFD, we'll see today how that easy it is, that you don't even need to distinguish the two in the CFD simulation in order to run that. And we'll show that today.
exactly. And so the other option was fluid structure interaction. So FlowEFD has a structural solver inbuilt that enables you to do those sort of analysis, even multi-phase flows, and combustion is also a capability within FlowEFD. All right. So David, how about you continue on with the
All right.
next section?
So next we'll go into meshing. And as we've talked about before, the meshing regime and meshing within FlowEFD is certainly a bit different than probably what you've seen in other CFD tools. So this is traditionally, as the office and I have mentioned, one of the trickiest and most time-consuming aspects of a CFD analysis. Oftentimes it can take more time to create the mesh and have the computer build the mesh than it does to solve the problem. And fluid solid regions using these special, I should say, smart cells, they can be contained within a single cell. So if you look at the image on the screen, you can see that these are all square cells of varying sizes, and they don't distinguish between fluid and solid. So that this is completely different. And the beauty of it is that the proprietary technology within FlowEFD allows splitting of cells into smaller subdomains that can be either fluids or solids. You can also have different materials within a single cell, which is quite amazing. Yeah, as I said, they have multiple fluid and solid control volumes. And one of the beauties of this is that you don't have to make any complex changes to your CAD geometry. You don't have to worry about those small little slivers of material in certain locations that create these tiny little elements that have bad quality and then cause the solution to fail. That doesn't exist here, and it's a major time saver. And really, it requires minimal input from the user to create a mesh. They also have the ability for solution adaptive meshing. So you can start out with a base mesh, and then as the solution progresses, it can do iterations of meshing and refine the mesh if there's high flow gradients or high temperature gradients in a certain location, so that it tailors the mesh for the most accurate solution. And that could be even bounded by, okay, I want it to refine the mesh, but I don't want it to do above 500,000 cells. You can say refine it until it gets to 500,000 cells and stop, so that you can really tailor this to what you have in terms of hardware needs, and make it work for you. But that being said, I can talk about it all day. Let's jump into it and take a look at what that looks like. So I have here another simulation that's been identical, but it's been meshed. It's going to take a second for it to open, just like the other one did, just to gather itself. But you can see other items here that have been populated in the feature tree. You can see our boundary conditions, including our heat sources, and some of the other things we'll look at here a little bit further down the road. And yep, oh, there it goes. It's going to load the results because that's where the mesh is contained. And before we do that, though, let's look at the meshing dialog boxes. Go back to my flow analysis toolbar here. And if I go to my global mesh that's been created and I edit my definition, I have two ways that I can define the mesh for this. I should say the base mesh. I can do it automatically or manually. And the way you do this in the automatic mode is you can start out with an initial mesh level. So if I show the basic mesh, this is a basic mesh in the three planes. It's going to give you a preview of what the basic mesh is, and then the solver, I should say the mesh solver, will go through it and refine the mesh automatically from there. And we're going to start with an initial mesh level of 4, but we could start out with an initial level of 7 or initial level of 1. We can start as coarse or as fine as we want for the mesh solver, and then from there, as I said, there'll be iterations performed to depending on geometry, spacing, etc., curvature, to automatically refine the mesh. But today we're going to do an automatic mesh of 4. However, we do have the ability to do a manual mesh as well, and we can actually, it doesn't have to be symmetric in the XYZ direction. We can change the number of elements that we have for our initial mesh in the X, Y, and Z direction. Say if you want to do some biasing of the mesh in certain directions, depending on which way the flow is going. You can also do automatic refinement of channels. So channels meaning between solid bodies. And you can do advanced refinement for small solid features, curvature level, as well as what the curvature criterion is. But just to take an idea here, you can look at, we can display the refinement level, our maximum refinement level based on our definitions that's overlaid. So the way the FlowEFD mesher works is, yes, it's just refining cells and it's subdividing them. And we'll see what that looks like here shortly on the mesh that's been generated. But if I were to look at this in a little bit more detail, and if I wanted to see what that looked like, yeah, I'm just gonna bring that down here on my screen. You can see that, these refinement levels, the maximum refinement level for the entire thing is 9 levels below your initial size. And you can see that can get very, very fine. And if that's what you need, you have the ability to do it. There's not many analyses out there that, especially for, commercial use and design use, are going to require that, but it is available. So as I said, we're going to use the automatic meshing today. We're going to keep that on the level of 4. I close that up, and we can take a look at what our mesh looks like. We'll just hide our geometry real quick. We have a couple of cut plots that have been pre-made to show our geometry, or I should say show our meshing. So we have a cut plane here through the YZ, the XZ plane with our meshing through the flow domain. And you can see here in the solid regions, we have a mesh level, initial mesh levels of 0. So that's it was our initial mesh size, and then it automatically refines down from there. And you can see that along where the fluid and solid interaction happens is when it starts to really refine itself. And notably, you can see that the mesh has to go from, it cannot skip a level. It has to go from 0 to 1 to 2. You can't have a 3 next to a 1 or anything like that. And one of the biggest benefits here that this automatically does is it improves the robustness and convergence of the solution. And that's something that you really have to do sometimes manually if you're doing a typical CFD mesh. And you have to make sure that you don't do that too much, or you can make the solution unstable. We can also look at the mesh for the other axis. So we can see the pins here, and you can see that everything's immersed here. You can see where the cells have also been divided between the solid and fluid regions. Go ahead and just hide these real quick. And as we said earlier about these smart cells, we have those smart cells. And if I can look at what the smart cells look like on the surface of the geometry, and it kind of gives you an idea of how well the mesh has resolved the pin geometry with the smart cells. And this didn't require any type of geometry decomposition on our part. This was automatically done by the mesher. But we still have some, for this analysis, we still have some good resolution on the surfaces here. The shape is, general shape is still there. If we wanted to go finer, we could, but we probably wouldn't gain any type of great changes in numbers for the results of the analysis. So this is a solution that's probably fairly robust and gives decent accuracy, but also doesn't take forever to solve. And that's really the key that we want by using this as a design tool, is we want to be able to get models that run fairly quickly, give us results, and can directly impact our designs to move the design forward. Another thing about smart cells that we can look at is looking at, as I said, there can be different materials within a single smart cell. And if I show this here, this is plotting the thermal conductivity of the solids in the mesh. And if I probe, I can use our probe tool here. You can see here, even though this is a single cell right here, this has multiple materials in it, because this is one thermal conductivity here, and this is another thermal conductivity, and this is another one here. And this is critical for something like this, where you have these very thin thermal interface materials between your components, and you don't want to have to individually mesh those, because those create a lot of elements and nodes quite quickly and can slow the solution down.
Yeah,
And
I
we don't
guess,
need to do that here.
David, to add to that, it's just an amazing technology that you can, you don't need to worry about meshing the solid fluid. It's one single mesh, and single cells can deal with multiple control volumes, up to 16 actually,
Right.
and which is just absolutely amazing, because now you no longer need to worry about, the issues with the mesh when it comes to overlapping bodies, and you don't need to worry about even just meshing the solid and the fluid separately.
Right. And just to piggyback off that, I mean, it's not like there's a huge limitation on like, oh, you can only have 2 different things per cell. 8, you can have, yeah, 8 different divisions, but I think you can have up to 36 different materials. So it's not like you're very limited here. This is gonna work for, probably 99% of most problems, or probably even more than that. And one thing I just wanted to go over before we close this out, as we were talking about how the geometry was overlapping earlier. So FlowEFD has something called material hierarchy. And in this case, the solid material hierarchy for the metal components, metal and plastic components, dominates over the O-ring components. So you can see here, we no longer have interference between the O-ring and the solid, and it looks a lot more like it would if the O-ring were compressed into the gland. So you're still getting the thermal contact between the O-ring and your other bodies, but you don't have to modify your geometry to do that. That's done so automatically. And you can do that with, if you're just doing conceptual geometry that's kind of dirty, and you know that there's going to be some overlap in places, you can set your material hierarchy and you just don't have to worry about it. So that's, believe, everything we'll look at for the meshing portion. And we'll go ahead and just go back to our PowerPoint here. And as we said, that this is, fairly easy mesh setup. It doesn't require a lot of complexity, and it's fairly quick. But also, as I said, very importantly, is that you can get good results without having to generate an enormous mesh that takes a long time to solve. And the mesh is very robust, and that can greatly affect solve time as well, especially for nonlinear problems. The next thing we'll look at is the FlowEFD solver. So the FlowEFD, like its meshing, uses its own proprietary solver. It exhibits robust convergence behavior due to a lot of the features that we just went over. It still uses the classical 3D CFD approach using the Navier-Stokes equations, but it implements wall functions using empirical correlations to resolve boundary layers at the wall. And oftentimes, or I should say always, with typical CFD, you would need to create some very, very fine inflation layers at the wall, especially if you had very high velocity flows, or something that had, just a fluid that had a very thin boundary layer because it was low viscosity. And you don't have to worry about that in here, so that makes the solver more robust, but it also makes a faster solve time. But the boundary regions are still resolved using empirical boundaries, empirical correlations for the walls.
Yeah,
So you don't have to worry. Go ahead.
Just to add to that, a lot of people have a big question to ask, in terms of turbulence modeling, what does it use? It uses a modified K epsilon turbulence model, which enables you to take into consideration the modified boundary layer that just David spoke about. So
Right.
it's not your typical K epsilon model. It's not your typical boundary layer model that, we generally are aware of, like log law or the all y plus function, but it has its capabilities of extracting from empirical methods of you know extracting the shear stress quite accurately. Uh, and I've done multiple comparative studies of FlowFD versus your top CFD tools, and the solution is not only robust and convergence behavior is fast, but it's pretty much accurate as well.
Yep. Um, so yeah, as we were just saying, that all this technology is meant to really take the load off the designer, let them run some analyses to change their design early in the design phase without a huge time investment, so you can get meaningful results to use. And that's kind of what we'll look at next in this piece of the demo is, okay, judging convergence for one of these solutions. How do we do that? Before typical CFD tools, you're looking at, okay, what's the residuals for my Navier-Stokes equations, my mass, momentum, and energy equations, and how do I interpret that? How do I know if my model's converged? And that's always one of the big things. In FlowEFD, you don't really have to think about that nearly in the same way. In FlowEFD, we'll be looking at in terms of goals, and these goals are really based off of what is your design intent for this product. So let's say the design intent we need to meet for this IGBT is, I'm gonna just go ahead and hide this plot, is that we need to make sure, let's say that these chips need to stay below 95 degrees C. All right, well, we want to know that. So we'll create something known as a goal that monitors the maximum temperature within the IGBT throughout the solution. And we want to know when our solution is converged that our IGBT temperature has reached a steady state. This is a steady state solution. And so if once everything gets to a steady state and the pressure on the inlet and outlet have reached a steady state, then we can be relatively confident that our solution is converged. So that's how we look at our models and how we judge convergence. But it's also directly the data that we use to inform our engineering decisions. So in this case, I'll just show you here, if we've already created our goals, but we have different goals that we can define up here. We have global goals, which applies to the entire solution domain. We have point goals that say if I want to look at the temperature at a finite point in space throughout the solution, I can do that. I have a surface goal where I can look at I've defined an inlet boundary condition for volume flow rate, but let's say I want to look at the inlet pressure and make sure that the inlet pressure has reached a steady state condition. I can define a surface goal that looks at the average surface pressure on the inlet, or I can look at the volume goal for just a single solid volume, which in this case might be our IGBT chip. Or finally, we also can use some of our previously defined goals to look at particular equations. In this case, for this solution, we have these goals that are already defined here, which is we're looking at the inlet pressure, which is a surface goal, the outlet temperature, which is a surface goal, the outlet heat transfer, the inlet heat transfer, and then we're also looking at the a volume goal, which is, this is actually a volume goal for the IGBTs, and we want to look at the maximum temperature in those. We also want to look at the maximum temperature within the diodes, and we also want to see what the temperature of the heat sink is. And then finally, we're using some of these equation goals to look at the pressure drop across this unit for the flow. And then we also want to look at the temperature change of the fluid as it goes through the unit. And then finally, the delta Q. So those are easily defined, and those are automatically looked at in the solution. If we were ready to run this, which we would be at this point, we could go ahead and go up to the run button. We could see here that it needs to run the mesh and rerun the mesh before the solve because there's been a change made. But one of the beauties of FlowEFD is that There's no core limitation. If you have some serious computing hardware, you can use it, and you're not going to have to pay extra to do it. If you have the cores, you can use them. You don't have to buy a special license. But you also, if you don't want to run this locally, if you have a compute cluster, if you're lucky enough to have that, you can run that on an external machine. You also can close the CAD environment while the thing is running so that you don't take up a CAD license. So these are all real big benefits. And the other thing I'll just look at here is, you do have some options to look at your, how the model converters. You can say, well, for these goals that I have defined, you can even define, which goals judge convergence, and you can even define the sensitivity. I want the delta P to be within 0.1 psi before it's considered steady. You can change all of those things depending on the type of the problem. But generally, the automatic is quite sufficient, but you do have the advanced capabilities there as well. And you also, as we said earlier, have the ability to do advanced refinement of the mesh as it's running, but we won't go in that today, but it's all there. So that pretty much covers the solver portion of the demo. If we look back, we've talked about how the solver is robust based on the meshing, but I'm not going to kind of keep reiterating that. But you can get a quick solve out of these. This solver for this model, I think the meshing took about 5 minutes and the solution took about 20 minutes. So for a CFD analysis, that's lightning fast for compared to a lot of other models. So finally, we'll look at the results visualization. Actually, not finally, this will be the second to last thing that we look at is the results visualization. And everything we've seen up to this point is really to get to this. And okay, we've set up this analysis. We want to know, how is our product performing? How is this design performing, so that we can make informed decisions on how we proceed? Is there a change that's needed? Is this thing ready to go to prototyping? We can use this to make that next step. So similar to FlowEFD pre-processing, the post-processing is performed within NX, also for the very intuitive user experience. The flow and thermal results can be viewed directly in an NX assembly. We can also create plot types. We can also use line geometry to look at results as things change over a linear distance. And we can also export our numerical data to other tools such as Excel or Word format in a report format to send to a customer or have for documentation later on for quick reference. So let's go ahead and take a look at that. So we have a couple of different types of results here. First thing we have is, you can see the mesh is considered a result, but the mesh can actually be seen before the full solution is run, even though it's contained in here. So we have cut plots, surface plots, iso surfaces, flow trajectories. The cut plots are looking at a cross section through the entire plot. Surface plot is looking at maybe an external surface of a solid, or maybe looking at the wall of where the fluid touches a solid. We can look at flow trajectories, so streamlines going through this entire thing. Another thing, if you're running particles or something like that, you have the option to do particle studies. It's really quite an advanced set of post-processing tools, and let's take a look at some of those directly. So the first thing we'll look at is the cut plot of the velocity. And I'm just gonna go ahead and hide our geometry to look at that. So we have a cut plot of velocity here. One of the nice things here is this cut plot of velocity, we have some streamlines that are also embedded. I'm just gonna flip this around here because I'm used to looking at it from flow going from left to right. And you can see our flow coming in here with relatively high velocity and diffusing through the pins and then accelerating again at the outlet. We can also look at the plot of the temperature. I'm gonna hide this one first. And here we can see the cold flow coming in at 65 degrees C and then exiting at a much higher temperature, much closer to, not a very high temperature change, but closer to 67 degrees C. And we can animate this really easily, so we can see the change throughout the flow domain. And you can see that it's hotter up towards the top where the chips are, and it's cooler down towards the bottom. take a second, iterate here, and I'll go back down. And we've already looked at the thermal conductivity. The next thing we'll look at, but also just real quick, if you want to, once one of these plots is created, you don't have to create new plots for each thing if you don't want to. I can just select temperature here. Let's say instead I want to look at the pressure drop. Select pressure, check, automatically updates the plot, and I can look at the pressure through the flow domain. From there, if we want to take a look at a surface plot maybe, and we want to look at maybe the surface temperature on the chip carriers and the chips, etc. We can do that really easily using one of our surface plots. And here we can see our temperatures are right at the 96 degree C temperature range. So that chip's getting pretty hot. If we were saying we wanted to limit it to 95 C, but as the flow traverses the cooler, you can see that these chips run a little bit hotter than these ones, which is what we would expect to see. Same thing, we can show the cold plate here as well. These, you don't have to do just one plot at a time. If you want to combine them, you can. You can add the casing we have here. If we wanted to look at the HTCs, heat transfer coefficients on the cold plate, we wanted to get an idea of what magnitude those were. We can do that here. You can see they're high right at the high impingement zone. We'll hide that, but let's say, okay, we want to show the temperature of the surface plate, but then we also want to see the flow trajectories around them at the same time. You can combine these plots to make some really nice visuals to be able to understand what's going on, and maybe share them with a customer if you're doing a design for a customer. We also can look at this in terms of vectors. It doesn't have to necessarily just be straight streamlines. We can put some vectors in here as well. All these can be animated. As I said before, we can do particle studies. The other thing, this is quantitative and qualitative data in these plots, but we also have the ability to look at some purely quantitative data as well, and be able to export that to whatever tool we choose. One of the first things we'll look at is that during our solution, we will be monitoring our goals. Those results of that, even though the solution window would be closed at this point, we can still view those. So if I open up these, we can go ahead and look at all the goals that we were defining and looking at. And if we show them, they're here in tabulated form. And we can see, okay, what the min and max value was, the units, the criteria for convergence. And we can also look at them graphically and see here the most important takeaway being that, okay, the static pressure at the inlet, you can see these have all reached very steady values. And we would be concerned if we were seeing, some oscillation here or something like that. And we were like, okay, well, I don't really see a steady state solution here. Maybe we need to figure something else out. These can easily be exported to Excel. And they do fantastic exports to Excel. They give the summary table, but also these really nice plots with all the data, and you can customize these as you want and use them in a report, etc. Similarly, if we want to look at, let's say, we want to look at the pressure drop linearly across the assembly, and we can just, we have a pre-created sketch in here, but if we have a sketch that we've created, we can view that, and we can also use that to look at some results as soon as it lets me open it. One second.
Yeah, while that, David, that's pretty amazing how the post-processing capabilities are. Just to add to that, one of the key things in what David will show towards the end is how you can essentially export all.
Yep. Oh, we lose you. I think we lost his audio for a second. But anyway, so there's this line that's been defined here that goes over the top of the pins and the location, maybe right at the fluid solvent interface. And we could define plots linearly across this. And this has been pre-created. So we have this XY plot here. I edit my definition, we're going to look at the pressure and temperature, and we just clicked on this sketch by going into our modeling, and that sketch is now selected. I can hit show, and we can see the pressure and temperature change on that line as it progresses down the flow stream. And we're seeing probably what we would expect here is some pressure oscillation due to the pins here, and also some temperature oscillation due to the pins as well. These, once again, can be exported to Excel just by clicking the Export to Excel button. Just a couple more things to show you here in post-processing before we jump into optimization. And the first thing being, one of the things that's new to Flow EFD is something called flux plots. And at first, this is kind of look like a spaghetti or spider web mess, but basically what these flux plots do is we can look at how the heat flows and how much heat flows directly between individual parts. So right now, this looks like kind of a mess because I haven't filtered anything out yet, but let's say I want to look at heat transfer, only heat transfer that's above 120 watts between components. If I do that, it filters this way down, and I can neaten this up quite a bit by just dragging and dropping here and showing how the heat flows between these individual components. And I can drag these around if I want, but I also can even select one and look at how much heat is coming from where in one of these components, and creating a little pie graph here. And so this is a pretty new, powerful tool, especially if you're looking at electronics where you have lots of capacitors and lots of little small individual resistors and parts like that. So this can be very well suited for looking at electronics cooling. Finally, you also can create automatic reports really easily, very detailed reports from a template, either that's predefined from Flow EFD, which we have here. I'm going to use this full report template, or you could create your own template too that's designed specifically for the type of analysis you're running, or maybe specifically for your company. And this is automatically opened now. And this gives, this is the full report, so this gives everything. This gives the version that you're using of Flow EFD. It's giving all of your boundary conditions, the entire extent of your domain, all of your materials. This is really a very comprehensive report. And this is sometimes good to just save with your results for a quick reference, so you don't have to open maybe the whole analysis if you're trying to figure out what this was. If you have a lot of work that you're trying to look back that you've done a long time ago or something like that. I know that was always a challenge for me, is okay, well, I've done all these analyses and it was years ago, and I'm trying to remember what the context was of, and I don't want to review the whole engineering report. I just want to get a quick idea of everything that's in here, and this is really useful for that. Lastly, you can export your results, so you're not constrained completely within the NX environment. Let's say you want to export pressures and temperatures for this to do a structural analysis or a thermal structural analysis of the pressures on the walls internally, but maybe also the temperatures on these components, and making sure you don't have some nasty deformation in these parts due to temperature gradients. That's all really easily done with an ASTRAN, or you can even export it to some third-party viewers like ParaView, which is a completely open source free viewer. All of that is included, so they really haven't locked you in to this environment either if you need to take it somewhere else. And that's pretty much it for our post-processing. The next thing we'll look at is our second poll. Yapis, are you still there? Oh yeah, he's still there. I think maybe we lost his audio, but that poll is up now. Maybe we can get a few more people to weigh in on that. So this poll is asking about using CFD analysis or as conjugate CFD analysis for electronics. And one of the major plugins that FlowEFD does have is used for electronics. So if you're an engineer out there working with PCB boards, this model that we're looking at today does have a PCB board, but it's very generalized to a homogeneous solid. FlowEFD does have the ability to use ECAD data to bring that in and create a PCB within this environment that includes all of the copper traces, all of your capacitors, resistors, everything within the PCB board to do a detail analysis, a multi-layer analysis of that PCB board with multiple layers. So that is a capability that FlowEFD does have as well. We'll kind of move on from there, and we will jump into design exploration, as we said. And we'll just we got about 8 minutes left here, so we'll try to get through this so that people can move on to whatever they have else for the rest of their day. We have those parametric options that are used within the NX environment, those expressions that can be used to drive a parametric study within FlowEFD. And it's, we're taking advantage of that CAD native environment for this analysis. We're also taking advantage, if we go into it here, looking at using one of the premier tools for design optimization that is a Siemens product, which is HEADS. So in this case, if we wanted to start a new design optimization, we could simply go down here and do a new parametric study. And let's say we wanted to optimize this design for reduced pressure drop, to reduce the energy needed for the pump, while also maintaining safe chip temperatures and maximum heat transfer. So when we do that, we have a couple of different options here. We have a what-if analysis, goal optimization, but in this case, we'll be using the multi-parameter optimization in HEADS. And this is just a game changer in terms of optimization, being able to use this natively within the HEADS environment, within the FlowEFD environment. So we have input variables, output parameters, our scenario, and then our results of our study. So we could look at boundary conditions. Maybe we want to figure out what flow rate we need or something like that. We have expressions. We also even have the ability to modify assembly constraints within an assembly. But today we'll be looking at expressions. So if I hit expressions, it's going to open all the predefined expressions that are within NX. And in that base plate, we can see those expressions that were previously defined. So we have the pin diameter, draft angle, and pitch. We'll select those. Those are what we're going to be using for our study. And when we need to define what range is acceptable for those, we don't want to just, say 0 to 1,000. We don't want to 1,000 millimeter, that's ridiculous. So we can define our bounds for these. And in this case, we'll be looking at a 2 millimeter pin, the smallest, and then the maximum will be 4 millimeters.
Yeah, I guess, David, let's just jump through some of these hoops to show them the parameters and the results, just because we have time constraints. So
yeah, so that's that. So we would define all our constraints here. In our output parameters, we would just use our goals. In this case, maybe we want to look at the pressure drop and the IGBT temperature, so we could select those, and we could select those, and then we could select a bounds for each one of those. So for the constraint for the IGBT would be an upper bound of maybe, let's say it has to be less than 95 degrees C. And we would also do the same thing for a pressure drop, limiting the pressure drop to a maximum value so that the study wouldn't go outside that range. So then here we would have our scenario, and we would select the number of calculations we would want to do. Maybe we'd do 40, that's 128 is a lot. And then we can select our optimization method. In this case, we would use the Pareto front. It would be the most economical in number of cores. This has already been run. If we open this up, we can see the results. And so this is all completely done. If we go to our scenario, we can see all the scenario is it's run, and we can see that which ones are considered an optimal point. We can see the study plots with the dependency, and we can see blue points are feasible and then green are optimal. In this case, if we took a real closer look at the data, we would see that optimum number 37 would be the best choice. And if we wanted to see what that looks like, we could just do create project, and it'll automatically change the CAD parameters in the model to reflect this. And we also be able to see the results too if we wanted. So it's going to go ahead and do that right now, and we'll see the pin geometry change. It's going to look a bit denser in terms of the number of pins, and be just about there. And yeah, so you can see there, bam. So you could, take this now and okay, say, start going to design review for this. You've got an optimal design, and we want to take it from here.
Yeah, and
So
I
this
think just to add to that, David, for a lot of times we have this concern that maybe designers won't be able to interpret the data, but as long as they have the design criteria, they can feed it into
right.
the optimizer to give them the best results.
Right. Yeah, and I think that's one of the major takeaways from all of this is that this allows you to use your design intent to optimize and maximize whatever you're trying to do. So yeah, so that's it for our demonstration. Just to jump back and say, kind of what we've gone over here is that, if we go back over these challenges, learning a new environment, it's not a new environment. You're doing this within the same NX platform or whatever, preferred CAD platform that you have that out of the 5 that are available. You don't need to simplify geometry for analysis. I didn't show it earlier, but you can even implement bring in a large assembly and say, I don't want to include any of these parts. I just want to include these parts. So you don't even have to delete geometry if you don't want. Knowledge on setting up the physics problem. This is fairly straightforward here. Implementing boundary conditions. You don't have to go too deep there. Discretizing the computational domain. You don't have to do separate domains for fluids and solids. It's all one domain. Resolving convergence issues. It's an extremely robust solver. It's certainly the most robust CFD solver I've ever worked with, and the meshing really adds to that. And you don't have to dig deep into the Navier-Stokes equations or be a numerics expert to do that. And interpreting results, we have a wide variety of animations, plots, but also, as I said before, and I'll keep harping on this, is that your results are directly looking at what your design intent is, and you're looking at those goals that you've predefined. And then finally, design optimization. We just took a quick look at that, but that's an extremely powerful feature that can save you a ton of time. I know in the past I've created CFD models and then say I'm going to create 10 versions of it for to try to create a sensitivity analysis and then go from there, and then I have to export all of that data within Excel to create an equation, and you don't have to do that. It's a lot faster.
Exactly. So folks, I know we've done a lot of polls right now. I'm just going to launch the last poll. These are the upcoming webinars. We're going to provide a recording online available, but I think I just want to launch this last poll, and it's essentially looking at what's the preferred methodology you would like for for you to get up to started with FlowFD. Do you guys want a one-to-one meeting? Do you want a technology benchmark where you do an evaluation or some sort of training, or just jump onto the software, or even just purchase the tool? So these are some of the options available, and what we'd like to do is take your responses and then get back to you. So for those who want a one-to-one meeting, we'll send up a follow-up email, technology benchmark. Maybe you have a test case that you want to analyze and make sure that this is the right solution. But then also a lot of our customers, and the majority of the success that we have seen is through software evaluation. I know we've reached the top of the hour. I'm going to leave the poll open for another 30 to 40 seconds. But essentially, David, first of all, thank you very much for this presentation. It's clarified a lot of my questions that I had about FlowFD as well, which is great. And I'm sure that a lot of the folks who've joined today would have learned a lot regarding FlowFD and its capability to push the boundaries of where we can use analysis, not only limited to expert analysts, but also for even CAD designers.
Yeah.
Wonderful. So I'm seeing a lot of votes come in. I'm going to give it another 10 seconds to close the poll and launch. I'll just share the results out here. But David, if you have any closing, what's next?
No,
so
just thank everybody for their time and your attention. And if you have any questions, you can ask us now, or you feel free to drop us an email. There's my contact information there. Feel free to drop us an email. Feel free to drop the office an email. or if you want to type a question in the chat real quick and you have a couple minutes, we can answer it.
Yeah, and so there are a few questions in the chat which I'll come to respond later on. I see one of the questions regarding a certification for webinar series. I'll have to get back to you on that. But if there are any other questions, yeah, here's David's email. Reach out to him, and we will set up that follow-up one-to-one session, or even set up an evaluation wherever for whoever those who are interested to look into that given package. So I think we've reached the end of our session. Thank you very much for your time, folks, and for your attention. And we're
Yeah,
looking forward for the next 3 sessions. More details on our website. Please don't hesitate to contact us if you have any other further questions. So I guess that's it from my end. David, anything else on yours?
no, thanks you everybody for your attention again.
Wonderful, wonderful. Well, thank you very much, and I hope you guys have a great day and a great week ahead.
Thank you.